Thank you for coming. I thank you for coming on time. I thank you for being energetic and enthusiastic. I hope that I can offer you something that you can value. I am not guaranteeing that I will download a book of reinforcement learning into your head. That is not my goal. If that's what you wanted, I apologize. What I would like to do in this time that we have together is to introduce you to the concept so that you can understand what it is and how it is not the same thing as building a classifier at a minimum. But what I would also like to do is to equip you with the tools so that you can learn for yourself. So I will show some pseudocode. The intent is that we get to those slides where we can walk through this pseudocode. And the Greek that is on it, yes, I think we have a pi. That's probably as much Greek as you will see on these slides. But the Greek that is on it, it's intended that you'd understand how to implement that in code, right? It is intended to be practical. I hope that I have balanced it well enough. If not, ask questions. If not, raise your hand. Let's have a dialogue and we can take this in a slightly different manner. All right. So first, let me introduce myself. I'm Sekou. I'm a research scientist based here in Nairobi at IBM Research Africa. My background is I'm an electrical engineer. Is there anybody else who understands what that means? Yes? Yes? Yeah. But guess what? I'm also a computer scientist. Is there anybody who understands what that means? All right. Now, my parents would have had a fit if I had told them that I also was doing math, so I just did a math minor. 2 classes away from being able to say I had a math major. But my point is this. I have had broad experiences. And one of the things that I can say, it consistently helped because you realize that in one class, maybe linear algebra, you're exposed to a concept in a way, and then you see the same concept show up in electricity and magnetism. Or you see that same concept show up in probability and statistics. The ability to see one topic from multiple vantage points, it is incredibly helpful. In that same vein, the ability to see one topic from multiple entry points from, let's say, many teachers is also something that I would urge you to do. Don't just say, I have checked the box, I did probability and statistics, I am done. Your job as a human being who is interested in learning is to understand that topic, that domain, from as many vantage points as is practical. So, for those of you this is their first introduction to reinforcement learning, please do not let it be your last. All right? So, we live in an age and a time where you have access to so much. What is on this slide right now, and I'll do my best to make sure that I can share this probably via Twitter. There are amazing textbooks that you don't have to go and pay Amazon money for. However, I'm not saying don't buy textbooks. Let me be clear. The publishers of these books, the authors of these books, have decided to share their content with the public because they would like to get engagement up. They want rooms like this to be 3 times as big, and they want people to not have access to a textbook to be a barrier. So if you can buy the textbook, definitely get it, because the internet is not always with us. However, each of these links is directly from the publishers or the book authors themselves. So we'll be using one of these books, Reinforcement Learning and Introduction by Sutton and Bartow, Luminaries in RL. One of the things that I like about how they treat reinforcement learning is that they bring the thing together, right? We'll see a little bit of that in the following slides. So, machine learning. Before we go to reinforcement learning, machine learning. Give me some of your favorite examples in machine learning. And yes, I do ask that you answer the question. It's not a rhetorical. Classifiers.
Hot dog or not hot dog?
Has anybody seen that example? A classifier that can identify whether something is a hot dog or not a hot dog? Right? There are so many of these and they're fun. But classic machine learning application, however, it is one type. It is classification. It's identifying whether out of all of these things, which of these have the same label as the others. Right? How do you build a classifier? Pop quiz. Okay, you have a data set.
Build a model with a certain hyperparameters.
You build a model before, wait, hold on. You go from data set to build a model with hyperparameters. I think we're missing a few steps, right? You have labels. So you're saying your data set must have labels. Is that necessary for classification? So we will come to that in the next slide. But I hear where you're going, right? Your classifier, this thing, it normally is a model of some type. If you give it input, it gives you output of the kind that you would like. You have to train it to do that. How do you train it? Well, there's magic that happens with training set, test set, validation set. Okay. Regression. Is regression the same thing as classification?
No.
Haha. There are some who say, maybe. In reality, it is close, but it is distinct. What's the distinction? Discrete. This notion, you can build a classifier that, quote, classifies things into an infinite number of sets, and technically now you're stretching in the domain of regression. But regression is more about predicting. That data set that you talked about, maybe that data set gives you information about some physical phenomena. The model is now allowing you to predict, given these features, what can I predict about these other features that I care about? Right? Do you need labels?
In regression?
In regression. I hear yes, I hear no. I love this. I love this. I will not answer that one, but I like it. All right, ranking. So this is another element that is, call it modern machine learning, right? You have 1,000 things that you can possibly see, 1,000 things that you can possibly look at. However, you only have 10 seconds, or you only have a screen that is, this screen is a little bit too big for me, but there's a limited amount of real estate that you have. You want to make sure that whatever you're showing is the best according to some metric. Ranking. Clustering. We like to do this thing. I don't know why. If you notice, it's a natural phenomenon that I still am trying to understand. Clustering. Human beings cluster in ways that I don't think they're even conscious of. But we like to write code that can cluster too. This is typically or prototypically one of the most common or engaging types of unsupervised learning, but it resonates with us in ways that, I'm still trying to. My point is, there are several different types of things that we're accustomed seeing as typical machine learning tasks. However, separate from the thing as a task, there is also this notion of, there is oh, wow, you cannot see. Trust me when I say these things are on the slide. There's machine learning, and then there's the opportunity to do supervised learning, unsupervised learning, and reinforcement learning. That classification task, you actually could perform it using each of these three. However, the framing of the problem would be distinct in each of the cases. Your goal could be to build a classifier, but you can build that classifier using each of these approaches. All right? What's the advantage of supervised learning? Why do we like it? You like it because you have labeled examples? Most people run away from it because you have, You mean you have to label 1,000? Who was it that was saying yesterday you had to have, so I met somebody yesterday, I don't know if she's here today. She smiled when she said that for my problem, big data for me is 200 or 300 samples. Yet these people are saying to train models you need 9 or 10,000, right? Labels are limiting, so that's one of the downsides. However, labels allow us to exert control. Labels allow us to say, here is what I want you to do. This is the gold standard. This is what I would like you to accomplish, captured in labels. And hopefully those labels are right, right? Based on that, go build me a model. Now we come to your model. Right? That's the beauty of supervised learning. However, if you have cases where maybe you actually have an abundance of data, maybe you are lucky enough to be in South Africa and have access to the square kilometer array, bunch of antennas pulling lots of data about things outside of our galaxy. Tons of data. Data that you cannot store on disk so that you can build your classifier, so that you can figure out if ET just made a left turn, right? You have to use unsupervised mechanisms because you cannot expect a human being to sit and label all of the data that is coming through. That's the beauty of unsupervised mechanisms because it can help filter the amount of work that a human being has to do, right? Unsupervised learning is useful, but again, it solves a different problem from the traditional supervised learning. Now, you also have this other thing, which technically isn't a thing, but it definitely is a thing, called semi-supervised learning. Right? So we just took our nice 3 crisp categories and we've said we're going to smush them into 2. Semi-supervised learning. So the elements of supervised learning and unsupervised learning that you use to address the same problem. I would argue that what you have just done is just split your problem into components, and they're unsupervised and supervised elements of it. So we still haven't violated the 3 categories here. Before getting into reinforcement learning, I'll ask the question that I know somebody... So, one thing I can add in this room is thinking, what about GANs? Where do GANs fit? GANs are amazing, right? Is GAN supervised learning? Is it unsupervised learning? Come back next year, we'll have a conversation. Reinforcement learning is something different from those 2. You can view it as an agent has the ability to teach itself. So it's self-supervised learning to some degree. I don't think anybody would give me too much trouble if I said this reinforcement learning is really self-supervision. But if I am the agent that's learning, how do I supervise myself, right? Think about your experiences having to teach yourself a content on your own, right? Maybe you pulled a textbook, maybe you found lectures for a class and you're like, okay, I'm going to teach myself quantum physics. Okay, I just aced my test, the test that I wrote for myself. How do I know that acing my test is actually a positive example of learning? It's not really, it's not practical. So there's this unseen thing in reinforcement learning that normally you get to maybe, I don't know, 2 or 3 weeks into the concept of, okay, there's this thing called a reward, which is coming from the environment. We'll get to what environments are. But this reward is critical. It is the only way that I have the ability to know whether I am supervising myself well. All right? If we're saying self-supervised learning, you have to say in the presence of a reward, conditioned on a reward, if you will, let me have that brief bit of probabilistic talk. If the reward does not help me to learn the task, then I will never be able to self-supervise. I will never be able to learn that task. Or, even more hilariously, maybe I might learn a way to address the task in a manner that nobody expects. And that commonly happens in reinforcement learning. Now, RL is old. And RL has been, I guess the word you can use, has been found or has been invented in many distinct communities. The one that I really like, which is so we know about artificial neural networks because that's what we do, right? Deep networks, they're ANNs, right? It's the same thing, right? What about the real psychology groups that talk about, no. We are really talking about neural networks in a practical manner. This neuroscience group. Sure, you made an approximation and you got some cool results, but you don't really know how it works and it's not really biologically representative. But that's cute, computer scientists. With that said, some of the findings that show up in RL actually come from these two communities, and they're distinct. They came through different mechanisms, different methods. Electrical engineers in the room, you know you had to do an optimization class. Sometimes maybe you got a really cool lecturer that even gave you the module on optimal control. Guess what? It's here. Elements of optimal control show up in this thing that we experience as reinforcement learning. Not going to dwell too much on it, but then there's this other element of learning, which any good RL textbook will cover. There's a coupling between learning and planning, right? But not content that I'd like to cover in an introduction, right? But there is such a thing as planning in reinforcement learning. All right, so brass tacks, reinforcement learning. You learn from interacting with something. So unlike your supervised learning case where you're building a classifier as an example of one type of supervised learning, you're not just interacting with a training set that is telling you ground truth and what the universe is, what you should learn, how the world should be related. Your job is to interact almost like a child or anybody engaging in content for the first time. Interact with your environment, figure out things. Hey, wait a minute, if I hold the mic here, I don't have to speak as loud. If I hold the mic here, I have to shout. I'm interacting with my environment, maybe sometimes unconsciously. However, if I am conscious about it, then I can now use the information that I'm gathering to better plan what to do. Interaction is key. I have to have a goal. Now, this can be really, really, really simple. My goal is to collect all of the coins. Think of the games that you normally see RL being applied to. Sonic. I want to get all the coins. Very simply framed, that's my goal. So if you see anybody playing Sonic and they're not getting all the coins, you know that they're not doing a very good job at the task, right? But what if your task was to drive on the streets of Nairobi successfully? How do you define that in an easy to state goal?
Get to the final destination.
Get to the final destination. Okay, I like it. Quickly. Okay. You must have driven in Nairobi before. Without accidents, I like it. You are cautious. Now, do you think this sequence of definitions of what it is to drive in Nairobi without accidents, quickly getting to my destination, do you think that there's a unique solution to that problem? No, I don't think so either. However, I do think if we were to quantify the goodness of a solution, of getting where I'm going quickly without accidents, maybe we might find that there are multiple solutions that have the same score. Now then we have a problem. How do I pick which one I want to choose? Let's put this in an Uber context. if I'm sitting in one Uber, I know how long it's going to take for me to get to my destination according to the app. And you are sitting in the Uber next to me. You also know how long it's going to take for you to get to your destination. I would like to find out if my path is different from your path. Will they be weighted equivalently? Will you score them the same? Maybe you prefer not to drive around pushcarts, borrowing from Aisha's keynote yesterday morning. Maybe you say, I want to go on the Eastern Bypass. It's possible. But what you're doing there is you are changing the definition for what a good path is. So it's no longer getting there quickly without accidents. Maybe you're saying getting there quickly without accidents, getting me as far away from pushcarts as I possibly can. The solutions that are developed from one RL algorithm, the same RL algorithm, might be extremely different if presented with one type of reward function than being presented with the other. This reward function concept is important. It links this notion of how you know whether something is actually attaining the goal. All right. I've implicitly talked about this. You have to interact. If you're not interacting, you're not doing reinforcement learning. That's just straight up. If you don't have something that says either evaluate policy, evaluate action, step, giving it an action, something that allows you to do something with an environment and hopefully get information back that is useful, you're not doing RL. So, RL is all about learning what to do in the context that you're in. All right? Let me repeat that. RL is all about learning what to do. Not what somebody else did, supervised learning. Not something amorphous about the universe and what things might be similar to each other and what things might be different from each other, unsupervised learning. Conditioned on the signals that you get from the environment, RL is teaching you what is the best thing that you ought to do. All right, I will skip these 3 slides because I think you get the point. RL is not supervised learning. All right, so this concept, the learner is not told what to do. There is trial and error, and here's a new concept which supervised learning can't really help you with. There's this notion of having a delayed reward, right? Delayed reward. Why does this matter? So, if I want to get to my destination without accidents really quickly, maybe it's better for me to choose to head away from the place that I really need to go, because there's a much faster route for me to jump on. So if I'm looking at just what would my reward be right now, maybe it's going to take me more steps or take me longer, at least it appears so at the surface. But because I went away from my goal, it now allows me to do things that I would not have had access to if I had gone in the general direction of my goal first. Delayed reward. For me to know that that is possible, I actually have to do something that may not seem initially straightforward. I have to both exploit what I know, but also explore. Now, on Sunday, Oliver and I were roaming, trying to find food. Anybody had that experience, trying to find KUCC, right? You had that experience. Any of you stopped and asked for directions? Any of you found those directions didn't help at all? All right. So there were two groups of us that left lunch. Both of us, independently, I would assert, we thought we knew where we were going. I was in a group that left after this first group. Why are they going that way? That makes no sense. Guess what this is? We are going to explore and exploit the information that we have. Now, somewhere in the middle, we met some of the people who were in that first group. They were walking a little bit ahead. Then we met the rest of the group, but we were now heading in opposite directions on the same road. Seemingly, we are applying different policies. If you're in a particular location, how do you know what to do? We told some of their group, follow us, we know what we're doing. And actually we did. Don't ask me how. But we did go through a process of both exploring the environment around us, because we had never been to KUCC before. And yeah, sure, you can say there's Google Maps and you can look it up, but what's the fun in that? But the combination of both exploring, predicting where we thought we would end up if we walked down a particular path. Sure, we can look up and we can see the tops of buildings, but you can't see a direct path to that building. Again, now going back to our deferred expectations. Explore a little, go this way, but you'd want to explore in areas that you think will add value for your future. All of these terms that I'm talking about, doesn't sound like programming, doesn't sound like data science, right? Innately, these are things that we do. We are already practicing reinforcement learning. We just may not have known the vocabulary for it. That is one of the reasons why this showed up in neuroscience, in psychology. Those who are studying biological systems, like us, are able to tell us that we are applying these mechanisms, we are applying these practices. But now, because there are CS and EE and math, we can now codify what we're doing in a little bit more formality. Final point. Unlike classifiers, unlike, let's say, ranking, most RL framings are really interested in the overall problem, solve the problem. The problem is traveling through Nairobi. It's not about identifying traffic lights along the way to Nairobi, or identifying road hazards along the roads, or identifying obstacles of a particular type. It's, I want to get entity from point A to point B. So it's a holistic view of whatever the problem domain is, whatever the problem framing is. And yes, you can use supervised learning and unsupervised learning in your RL solutions. So some of you have already flipped to the back of the book and you have seen that there are deep RL. It's a thing. It's not substantively different from RL. It's some of the elements of RL are now replaced by functional approximation using a neural network. All right? We still okay? All right. This picture, which I hope you can see at least, is the canonical reinforcement learning picture. You have an agent that acts on the environment at some time t. All right? When that agent acts on the environment, something happens to the environment. Hopefully, that thing that happens to the environment is detectable. If it is detectable, you will notice a new state of that environment, meaning the environment was in one state prior to the action, and it changes to another state after the action. In addition to being able to get the state of the environment after the action, you also have the ability to know reward. Or how good was that action? Measure of goodness. That is passed to the agent, and now it determines what's the next action I do. Now, I said that the agent selects an action at time t. Did I say anything about whether time is discrete or continuous? Did I say anything about whether the actions are discrete or continuous? Did I say anything about whether the state? No. This is how reinforcement learning can be more complex depending on the context of the problem that you care about. All right? So, time matters, but I haven't limited anything else. What I would say is that you are acting at intervals of some finite opportunity. All right? You're acting, maybe your delta t is really small, maybe it's on the order of milliseconds. Some problems, maybe if you're doing, I don't know, an application that deals with advertising and ad revenue, predicting ad revenue, or predicting something around economic state or trading, maybe your delta t's in that case, the time between t1 and t and t plus 1, right? Those can be really small. But maybe you're dealing with a case like the case that we're exploring for the malaria hackathon. In that case, your times are years, on the order of years, right? Or can be on the order of years as we're framing it today. All right. So if you ever see this picture, somebody wakes you up at 3 o'clock in the morning, shout out reinforcement learning. What's the state? What's the reward function? Right? That should be your instant response when you see this image. According to Sutton and Bartow, there are only 4 things you need to know as elements of RL. I've added 2 that I still think need to be on this slide, so I won't let them go. This policy thing, what do you do? That's what a policy captures. Now, what do you do can be conditioned on what state are you in. So for example, I am facing this way, you are facing this way. We're in different states, very grossly different states. Each of you is also in a different state yourselves. However, if I wanted to get through that door, the actions that I take would be substantively different from the actions that any of you would take to get through that door. So the probability of me selecting an action like turn right is much higher than the probability of you selecting that action. Right? That's this notion of what is captured in a policy. What's the likelihood of you picking any given action given what you are trying to accomplish? Reward. If I did turn right, how good is that action in helping me get towards the door? If I turned left, chances are that would be generate a lower reward, unless there was some kind of elevator outside that would get me outside more quickly. But reward, it quantifies this notion of what is good. Metrics, we need metrics. Value. So what if I don't get the reward immediately? What if I only get the reward when I get to the door or when I get outside? How do I then infer, well, did I get the value because I slid from there to there in step 1? Or did I get that value? Battery. That was quick. Or, good? Okay, I can just talk loud. Or did I get that value because when I got to the door, I actually turned the handle 3 times clockwise? This notion of value allows us to interpolate what happens in between the times, thank you, in between the times that I did all of my actions and actually got the reward that I cared about, right? So value, it's a more abstract concept than reward, but it's determined, it's calculated, derived by knowing what rewards I've gotten so far. This concept of a model is a term that troubles me because it is very hard to define what a model is or isn't, and everybody has their own definition. But from our perspective, the model is an approximation of the environment. Right? We may have a very simple approximation of the environment, we may have a very complex approximation of the environment, but the model is an approximation of the environment that helps us do something. And I won't let state and action go away. These are inherent to any conversation about reinforcement learning, right? The representation of the state might make a problem very easy to solve or incredibly hard to solve. Same thing with the actions. I promise I'm not touching any wires. Your choices as a data scientist, as a decision maker, a person writing code, your choices in these spaces of how you define your state, how you define your actions, no matter what the environment looks like, can make a problem much easier to solve. Maybe it also makes the problem very quick to solve. So sometimes when people talk about the framing of a problem in a particular way, their solution, they're still trying to get the solution you want. But the way that they go about it may be very different from the way you go about it. So don't be afraid, all right? Once you understand how you are choosing to represent your universe, what do your states look like? How are you defining an action? Once you understand that for your problem, keep going. Somebody else attempting to solve the same problem. All right, so somebody else attempting to solve the same problem that you're working on, they may choose radically different things to do as far as their states and their actions. But that's okay, right? Once you understand how you are framing your solution and you understand the implications of making those assumptions. So for example, if I had, let's say hypothetically, an action space where I'm trying to decide, do I give everybody in Kenya a bednet or do I give nobody in Kenya a bednet? And I have defined that action space as a range from 0 to 1. How many possible options do I have? Infinite. Anybody has an infinite computer around? Just sitting in their back pocket? No? No? One person can choose to use a functional approximation of infinity that looks like this. I will use two numbers, a mean and a variance of a Gaussian function. I have now translated this infinite space into two numbers that can somehow give me something useful. Somebody else may say, well, I'll take that space and I'll just quantize it, just break it up into, I don't know, intervals of 0.2. That's now my space. Very different framings of the problem, and each assumption or each choice will have consequences that are distinct. But I have to make that point for you who are encountering this. Maybe you look at somebody else's solution and you're like, I have no idea what they're doing, why they did it. That's okay. You can choose to represent your actions and your states in your own way, and it still should work from a reinforcement learning algorithm perspective. All right? So don't be afraid about that one. So the fine leaves you won't be able to see. We started, again, using Sutton and Bartow. The canonical example that they used is tic-tac-toe. It's a really simple game. Everybody knows how to play tic-tac-toe. Everybody knows how to win at tic-tac-toe, right? Right? Anybody willing to put that to the test? Like, no? Okay. All right, well, I won't put anybody on the stand. But there are definitely ways that you can represent somehow that I cannot lose at tic-tac-toe. Right? It's much easier to say, oh, I know how to not lose, than to say, I know how to win tic-tac-toe. But tic-tac-toe is a very simple game. It only has 2 to the 18 possible board states. It's a very simple game. Here is a tree structure saying, if I started from this board state, that's the root of the tree. What are the possible actions that I can make? There are a finite number of actions that I can make as a tic-tac-toe player. If I were to make that action, there's a new state that would be created. Guess what? I have just interacted with my environment. By playing, in this case, if I was O and you were X, you have played in the center spot, a really coveted spot from all accounts of tic-tac-toe strategy. I played in the spot next to that, horizontal left. I have now created a new board state. However, that is only one of a possible set of places that I could have played. That means that that was only one of a possible set of states which could come next. Bless you. After I have played in that really nifty spot, Amy played top right. Oh boy, I'm in trouble. Why am I in trouble? Because, not RL related now, Sekou the individual knows that the goal of tic-tac-toe is to stop Amy from getting 3 in a row. That particular state allows her, possibly in one move, to get 3 in a row. So intuitively, I know this is a bad state for me to be in. If I had to play, I want to avoid this state. Question here.
What is the reward in the second and the third state?
There are no rewards as yet. In the tic-tac-toe concept, you only get the reward when the game is over. Maybe you get 1 point if you win. Maybe you can set up your reward function where you get -1 point if you lose and 0 points if you draw. However, you can also set this up that you get 3 points if you win, 1 point if you draw, and -2 points if you lose. Right? Those are 2 valid approaches to setting up a reward function. Each of those reward functions might end up in algorithms that learn to do different things because the pressures that are providing the only source of input, reward function is the only input that you have, are different. But I'm happy you asked that. You only get the reward after getting to the end of the game. So when I'm saying that I am nervous because Amy now has 2 in a row, that's because I know what comes next. Her job is to get 3 in a row, so this must be a good state for her. I have projected what she wants to do into the future and then backtracked to say, well, if she wants to do that in the future, then maybe this is a good state for her. Maybe that's why she chose to play in that location. All right? You see how I'm using the concept of actions, states, reward, in this case a deferred reward, and I didn't use the word value, but I implicitly referred to this state being high value for her because it will help her get to the reward she's looking for. if I was building an RL agent to solve tic-tac-toe, maybe I just play a bunch of games. And in the process of playing these games, I keep track of all the states of everything that happened. So literally, data collection. Then, after playing a bunch of games, I start to develop maybe something like a probability. What's the probability of winning if I'm in this state, given what I've seen in all of these games that I've played? I can use that information, I can build up knowledge about the game of tic-tac-toe, aka my environment, and I can use that knowledge to figure out what's the best action for me to choose at any point in time. So, doesn't matter, you wake me up at 3 o'clock in the morning, give me a board, haha, I know exactly what to do. Now, I may be wrong. So hopefully, if I am playing and I'm getting all of these traces, all of these examples of tic-tac-toe games, hopefully I'm playing against somebody that I can actually learn from. Because if I never have a chance to win a game, then I'll never know what it's like to do something useful. Sounds kind of sad, I know. So it sometimes is really critical that you, if you're building evidence, you're learning, that you're playing against an agent that is not perfect. Sometimes they make mistakes. When they do make those mistakes, hopefully you can learn to capitalize on those mistakes. Otherwise, at best, you'll just learn to lose gracefully. All right? Are you with me? Do you get the concept now of how you can use evidence by sampling the environment, in this case, playing tic-tac-toe, observing which states are more correlated with winning, and which states are more correlated with losing. In this case, Amy just beating me hands down every time we've played tic-tac-toe. Right? That is what reinforcement learning is really about in terms of the framing. Everything else is noise. Okay, not everything else. There are many critical things about RL. This notion of, let's say you have all of these possible choices that you can make. How do you know you're heading in the right direction? Not in a gradient descent kind of right direction, but how do you know that the actions that you're taking, whether it's in the short term or the long term, will actually get you towards your goal? All right? How do you know that the algorithm that you've implemented is in the limit or whatever other mathematical category you'd like to add, will get you to the goal that you actually want, as opposed to it will get you close to the goal, but never actually to the goal? Right? These are concepts that, as you spend more time in RL, that's where the magic comes in. So, yes, you're learning how to frame the problem. Yes, you're learning how to, maybe you are the one who is creating your reward function, in addition to the one who is creating the representations of the actions in the states. But now you're also asking the question of, if I make this assumption about how my algorithm ought to work, maybe that means that it will take me 3,000 samples before I can be confident that my algorithm will get to convergence. But if you had made a different decision, maybe it will take 1 million samples. Back to that problem that we have in other areas of learning. All right. So, if you were playing tic-tac-toe, here are a few examples of things that you could do to that RL algorithm that we just talked about that can help it get better. Instead of using all of the possible representations that I talked about, 2 to the 18, maybe you get smart and you realize that there's repetition. Maybe you can say, hey, how many distinct states are there of this board? And you might find out that, oh, it's only on the order of 300,000. Oh, well, that helps, because it now means the number of states that you have to keep track of is smaller. Okay? Well, is there anything bad that can come out of having a smaller number of states to keep track of? Seems like a good thing, right? Don't have to worry about how much RAM you have in your computer anymore because you're now using less of it. That's great. No need to use a GPU to beat me in tic-tac-toe. Right? Sounds good, right? But maybe by reducing the state, I have now actually created an opportunity for there to be uncertainty about which one of these I really am in. So yes, it may seem as if the state can be reduced without loss, but if I am reducing the cardinality or the dimensionality of the state, meaning how many distinct states can I be in, maybe I might make it easier to get two things confused that really don't need to be confused. It's possible. Always have to keep your eye out on that. Randomness. Randomness is good, right? 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 No? Yeah? No? All hail randomness. Randomness saves our lives. Yeah? Okay, maybe this is lunch talking here, but come on. Randomness can be incredibly useful, especially when we don't know ground truth, right? Randomness can help us get out of a local minima or maxima, depending on whether you're math or industrial engineering, right? Randomness can be our friend if we are good to it, because there is such a thing as too much randomness. One of the things, and I didn't dwell on it, remember I talked about exploration and exploitation? In the algorithm that I was presenting, you want to explore a little bit. The way that it's presented in many cases is 10% or 0.1, right? So 10% of the time, you explore. The rest of the time, you exploit. What if 90% of the times you explore? Might that be a good thing? You get to know more about the world, right? Yeah? Seems good? But what about you getting to where you're supposed to go? You might end up in Mombasa when you're supposed to be in Nairobi. So there is such a thing as too much exploration. Yes, you want to explore a bit because it helps you build knowledge about the states of the world. If you always did the best thing as far as you know today, which some would call the greedy approach, you will be limited because there'll be states that you will never be able to get to. And maybe that's the state that will allow you to win the game in 3 moves. However, if you explore too much, you're wasting time. Maybe you're making it more likely to get yourself in a state that will guarantee that you lose. You have to balance exploration and exploitation. Now, the final thing I would like to add is, have you ever looked at somebody else and learned something from them? Yes? What kind of things are those? Give me an example. Yeah. You learn to dress by looking at somebody else. Okay. All right. Come on, talk to me. Give me another example. Yeah. Dancing. You learn to dance by looking at somebody else. These 2 examples I like. I like where this is going. You learned to do your hair. I'm saying things that you learned, not things that you like. You learned to do your hair by looking at somebody else. Okay. I would assert in each of these 3 cases, you didn't actually learn to do it by looking at somebody else, but I would assert that you were inspired to do what you did based on looking at somebody else, but you had to do it yourself. Like literally, in your case, you had to touch your own hair. And maybe in the process of touching your own hair and doing your own hair based on whether it's YouTube or looking at somebody, you're like, hey, wait a minute, you made this seem so easy, but this is how I do it. Maybe you accomplished the same effect that they did, but your technique was different because your hair is different or your hands are different. Your goal in each of those cases, I assert, Your goal was to mimic what you saw to some degree, but you made it work for you because you have no clue exactly how they did it. So, looking at somebody else, you can infer things. Maybe you can even learn what might motivate you. But doing it yourself with that in mind is what allowed you to do it and to be able to do it well. A variation of it, if we're playing tic-tac-toe and we're collecting traces of games, does it matter whether that game was a game that you played or I played or anybody in this room played? No. You literally are just saying, here's evidence on a board. That evidence is evidence that couldn't have been generated 2 years ago, yesterday, by somebody left-handed. It doesn't matter. It's evidence. You can use that evidence and infer what might be good for you if you were to play. However, it's not always the case that it actually would be good for you because you are a different agent from them. All right? It is possible, and this is this last point, it is possible to learn from yourself, like you can practice by yourself. It is also possible for you to learn from other people. But that mapping, that translation from what somebody else did to what you do, there is an extra step there that is sometimes invisible and sometimes extremely frustrating. And I would argue, learning to ride a bike, yeah, you can see somebody else doing it, but there are very few people on the planet that can then get on a bike or fly a plane based on looking at somebody else do it. Now, with that said, there have been applications of reinforcement learning where you are observing a helicopter fly, crazy acrobatics, maybe upside down. Based on observations of somebody else flying, you are now using that as evidence, something to tell you what should be good, what should not be good. Again, not supervised learning, right? Not supervised learning. But you are using their states, their actions, and what you believe their reward was to build your own understanding of the relationship between states, actions, and rewards. All right, so I want to take a break, just a stand-up break, but before, just know that it's coming. This concept of here I have a squiggly line, but here I have a, let's call it, a discretized line. This might be a representation of the value associated with a given state. I am sampling through interacting with the environment, and I'm saying, okay, I know that this has low value, that has high value, etc. If the number of states that I have is infinite, maybe I end up with trying to approximate something that looks like this. Maybe. Do you know of any tool, technique that can help, like some kind of functional approximation? Anything? Universal approximator, even, that might help you approximate a really large search space or a state space. Yeah? A neural network. Fourier series is also there. But we're in deep learning Indaba. Let's keep the Fourier series talk down and let's talk about neural networks. My point is this. This is one example. This notion of saying, if you have a bunch of states, and let's say there are many, maybe you can use a neural network as a functional approximator to allow you to learn the relationship between the state and the value of that state without having to keep an infinitely long table. Right? So you can see exactly how we can now slide some supervised learning into this reinforcement learning conversation. But be very clear, it is specifically so that you can do a functional approximation, and that functional approximation has a role in reinforcement learning. All right? All right. Let's skip to the break first. For the break, I have my friend here. So for the duration of this video, I would like you to stand up. Hold on, is the video playing? Oh, man. All right. The video is not playing. It is what it is. But I would like you all to stand up. Oh. I would like you to turn around and have a conversation with somebody, asking one question and giving them one answer. So each of you has to ask a question. Each of you has to answer a question. Let's keep it in the context of reinforcement learning and what we have learned so far. One question asked, one question answered. These images were generated using applications of reinforcement learning. It may seem crazy. You can sit, you can sit. All right. These are agents that have learned to, quote, walk, run, jump, slalom. Allegedly, this is the pinnacle of reinforcement learning today. Okay, not really. Do you think that you can write the code to control 27 degrees of freedom? Probably not. However, RL, through interacting with an environment that looked like this, that has physics in it, has somehow generated controllers or generated agents that can do something that resembles running. Granted, there are very few people who would run like this. Remember the point that I made really early about your reward function being critical? If your reward function is set up in a manner that you can do well without actually accomplishing the task, let's say the task is running, but you run really fast, meaning you get good rewards. I can play it again. You get good rewards by sliding, sliding, sliding. Or maybe you get rewards by jumping, even though you're not really positively supported for jumping. All right? The signal is the only thing that is used to teach the agent what to do. It is very difficult to then go in, almost as hard as figuring out which weight does what in a deep network. Which example is the actual example that led this thing to figure out that this is how it should run? Which set of examples are the things that led this agent to figure out that this is how you implement ducking? You don't have to worry about those things. The agent is choosing what actions to do with the environment based on exploration and exploitation. It has to trust that reward signal. Now, with that said, bless you, there are many times that we ascribe capabilities to the things that we're seeing here as, oh yeah, the agent learned to put precise foot positions because that's exactly what it was thinking about. That's not what's happening here. There is no thinking or reasoning. That's a different part of artificial intelligence. This is literally saying, give me a reward associated with the performance of an action or a sequence of actions. Let me use that reward to infer the value of a particular action in a given state, a particular action in a given context. All right? If you Google reinforcement learning and walking, there are many other things that you can see which will brighten your day. All right. So, the reality check. There's a lot that people have said reinforcement learning does. And reinforcement learning has performed better than human beings in many tasks. However, it's not, quote, a done deal. You can't say today that reinforcement learning can be used to solve every problem that is out there, even the ones that are well framed in a reinforcement learning context. Right? There is still a lot of trial and error. There is still a lot of art around this science that we're in. You still have to implement multiple algorithms, and sometimes, maybe 20% of the time, Bender would say 40% of the time, 30% of the time. RL is definitely something that we should use, but we should use it under proper advice. The point is, it's a technique, just like supervised and unsupervised learning, that is in our arsenal. If we can frame a problem appropriately, and we understand how RL can be well suited to it, if you have something that requires sequential decision making, if you have something where an action today impacts the possible futures that can exist, if you have something where there's this notion of a delayed reward, let's talk RL. Don't just do it blindly. There are many problems that you can use RL to solve. However, somebody else has solved it much easier just using deterministic optimization. Somebody else has solved it much more elegantly with a closed form approximation from control theory. All right? It can help us. It is cool most of the time. It is well suited to many types of problems. However, any problem that we can address using RL, I guarantee you there's a way to make an approximation of that problem that may make it seem as if it's well suited for another problem formulation as well. Right. So, I wanted to still leave time for questions, but there are a couple of things that I do want to mention. Bandits, so basically greatest hits kind of concept. You'll hear the term multi-arm bandits, and it sounds cool, kind of. Right? What is a bandit? Anybody have a sense of what this multi-arm bandit concept is? Yes, it's on the screen, but talk to me. Anybody new about this term before? Ah, okay, let me start there. All right. So the concept is this. You interact with the environment and you get a reward. Sure, there's a state somewhere in there, but we don't talk about states. You just literally say, I have an action I can do. It's one of n things that I can do. When I do that thing, here's what happens. Now, what happens if I do that thing 5 times in a row? Maybe I get a really great reward when I add it all up. But maybe the 5th time, it causes me to get a really large negative reward. That's this notion of interacting with the environment, just as we were before. And now I have the question of, here are the many things that I could do. And now I need to learn what's the best sequence of things for me to do to maximize my reward. RL all day long. The multi-arm bandit framing is something that is common. It's normally the closer to the beginning of the RL textbook than the end. But it's one of those environments which you can readily try things out. You can readily explore. So know that its history, the name of it came from slot machines. So basically think of going gambling. You have many different choices of machines that you can play. Which one do you play? Well, maybe if you played that one, then you might have won $1 million, but you didn't. The person who came after you chose to play that one, and they won $1 million. Does that mean that if you play it, that you will also win $1 million? No. But maybe if you play enough, you will learn some kind of information. Maybe the pattern or the cycle is something that can be inferred over time. And maybe if you had an unlimited amount of money to play slot machines. But that's the concept of the Bandit problem. And there are many formulations that this is actually a really cool initial introduction for. We talked about exploration, exploitation. The one thing that I do want to mention, one thing you also see commonly, remember I talked about value? And your goal is to figure out what's the value of a given action? I would say 20% of so-called, quote, tabular methods, they're just coming up with really cool ways to come up with what's the actual value given evidence. So there would be some kind of new estimate of Q, don't have to worry what Q is. There's some new estimate of Q that you're trying to figure out. And that new value, that new estimate of Q is derived by the old estimate of Q plus something. Does that seem familiar? Error, target, update rule, simplex. These terms sound familiar? This concept is pervasive. But the notion of estimating your Q, estimating the goodness of an action, or estimating the goodness of an action given that you're in a particular state, that's basically, I would say, 30, 40, 50% of reinforcement learning textbooks. Because one person says, oh, here's this really amazing update rule that I have invented. And that rule says that my new value of Q is my old value of Q plus some 1 over n. Sounds like an average, right? 1 over n reward minus my old value of Q. But somebody's like, okay, that's nice. That's nice. That's nice. How about scrolling forward. How about we use this amazing update rule? We take that old value of Q and then we add this stuff to it. Same structure. So instead of the 1 over n, now you have it framed as alpha. Alpha is generally a number between 0 and 1. Well, 1 over n is probably a number between 0 and 1 if 1 is positive. There's structure here. So alpha, reward, just as we saw before, and then something relating to our old value of Q, right? Different algorithms or different methods, you flip through the tables of all of these textbooks. It's really just another method of saying, how do I update my Q given new evidence, given new opportunities to sample the environment? So most of those equations look like this. You initialize something. In this case, you're saying, for every action, I set the value to 0. I set my Q to 0. For every action, I also say, I initialize by setting the number of times I have evaluated that action to 0. Seems like a nice thing to do for initialization. But somebody sitting next to you might say, well, what if I want to initialize Q? What if I want to initialize it to my favorite number, 15? Is that okay? Sure. What's the implication of me doing that? It means that if I know nothing, I am very optimistic that this action that I have never tried before will have a value, or have a Q, a goodness, a value of 15. Until I find out that that action is bad, I will assume that this is a positive thing. Only when I actually sample and I get something to update that value can it even go down. So it's a very optimistic view of the world. Right? That's an example of how one choice of an initialization might change how your algorithm works. But guess what? Each of us in this room has the ability in our favorite language, even if it's not Python, to implement this algorithm and every variant of this algorithm. This, as I said, is primarily telling you, how do I update Q? How do I update my understanding of how good a given action is? So I'll just show one really wild one, just so that you can say that I've seen something wild. Salsa, it's there, it's in the textbooks, it's everywhere. But trust me, even if you have never implemented a Q learning algorithm in the past, once you understand the very simple Q table, the concept of how I'm updating my Q table based on evidence that I get when I interact with the environment, this is just an implementation step. The science or the deep inquiry comes in now you can understand, if I made this choice, if I chose to initialize in this particular way, maybe instead of initializing to 15, maybe I initialized random values for my Q. Are there theoretical guarantees that come from that? Yes. Does it mean that I may converge faster or slower if I make one choice than the other? Yes. That's where the deep insight comes. That's where the 2-3 course sequence in RL allows you to take this knowledge, make it your own, and allow you to be able to win Zindi challenges on reinforcement learning. All right, so I will stop here, and some of you got to ask questions in a friendly setting, so hopefully this has now warmed you up to now me asking you, do you have any questions? Let's talk. Yeah.
Thank you for the presentation. So I just would like to know if an agent wouldn't be able to reach its goal, but it has like a very high number of free words. Would that be like, is it possible to say that now the agent has failed and all the solution is cancelled and we don't have to go through all the steps that or actions that we've gone through from the beginning?
So let me ask. So if I'm understanding the question, you're asking if it's possible that an agent can spend, let's say, 100 or 1,000 steps interacting with the environment and not get to the goal that it was intended to reach. Yes, that is possible. All right? So for starters, yes, it's possible. You would hope that it's not, because let's say your task, you only generate rewards if you get to the goal. If you never got to the goal, then you'd never have a way of knowing that any of your actions were helpful. All right? So there is exploration. And if your exploration does not benefit you, then you have a problem. Right? So it sounds a little bit gloomy. However, if the problem was framed a little bit differently, where it's more likely that you actually can attain a goal, the question is, how do you attain that goal in a manner that is practical? There are many failed reinforcement learning applications that then become viable by literally changing the problem that you have to solve. So maybe instead of having a robot that learns to walk, maybe you constrain it to say, I have a robot that will learn to walk in a plane. So yes, there are 27 degrees of motion. However, the robot can't fall to the left or the right. Oh, look, now we can make videos and robots can walk all of a sudden. Well, what are the assumptions? What are the limitations? You have to always look behind. Another element of this, which is, I think, a point worth making again, a lot of reinforcement learning fails. A lot of it fails. There's another element which I didn't really mention in terms of sample efficiency. How many samples do you actually have to do to generate these robots that can walk, jump, and hop, robots that can fly? Many. So in many cases, you're dealing with things that are optimized to run for, let's say, a few tens of seconds. Based on that, you run these, so most of these kind of RL challenges are running for the order of weeks or days, like days or weeks, based on thousands or hundreds of thousands of samples. The challenge that we're doing at this competition, at this conference, is not like that, because we don't have that long to wait. But also, it's also not practical. There are many applications where the cost of a sample is really high. So you want to be very sample efficient. That's another element. So depending on which algorithm you pick, you may have implications for sample efficiency. That might mean that, yeah, we just can't solve this problem with RL as it's currently framed.
Okay. I have another question.
Yeah. All right.
So can we convert RL problem into sequence modeling? Like, for example, when we try to find the relationship between the current state and the next state, and then maybe we can find a way to flag the reward into positive or negative number, and then we use it as many-to-one modeling.
I see where you're going. So there are two things that you're talking about there. Short answer is it's possible to do what you're doing, what you're thinking, because I think I know the backdrop of where you're going with the question. But sequence modeling, in essence, by itself, we can say you're asking if it's possible to build a model of the environment, assuming that it's sequential. So basically, you can use any sequential modeling technique. And you can now use that model to figure out what to do. So in essence, you're saying you have the environment, you interact with the environment, you learn from the environment, you build a different model, you optimize that model, or you figure out what's best to do with that model, and then you act in the original environment based on what you learned.
Yeah.
So the short answer is yes, that's possible. So I didn't dwell on it, but there is such a thing as model-based reinforcement learning, and that's what you're describing. Yeah. That is not the only type of RL, though. So one question, can you come up? And if you need to switch rooms, feel free. I will not be offended. But the bell is ominously tolling.
Yeah, thank you very much. Cool. First time I actually looked at your house of Remy was similar to simplest algorithm.
Okay.
It's got parameters behind it.
Okay.
I was looking at the rats and the reward system.
Okay, yeah.
So I want to ask a question. Rather than it be random, can we define the number of actions, like assign probabilities to the number of actions? So it doesn't just pick a number. So when you define probabilities, I think you have limited the sample space that it's going to move into. So it won't exceed that sample space. So it has to pick in individual values from that sample space.
Yes. So let me, and you can come up. You can come up. The short answer to that question is that that is profound insight, and yes. I think I have it here. Well, the point is, as you learn this Q function, maybe your actions are selected based on the magnitude or the goodness of what you have learned. So you're not just randomly picking any action, but your random probabilities are based on the Q that you know for that state. So your actions are distributed based on the goodness as you have learned over time. So yes, it's not completely random in any of the cases. So one thing I can add easily is there's something that you said that is profound. As a person creating an environment, you have your own states and all of these things that exist in the environment. As the person creating the RL agent, you have your own states, right? You can define your states. Hopefully it will match to the environment that you're using, but you can define your states independently. So that point is important because maybe this is a very complex state space, but you can optimize or you can find sequences of actions that you can perform with a very simplistic representation from the outside. So that's one, it's possible. Getting to the real meat of your question is, it's hard. So the question really is, how do you package an environment in a manner that is useful? How do you package an environment in a manner that it can actually help somebody who you don't know to solve a problem that you would like to help them solve? As a team, we're still trying to figure out what's the best way to do these things, and we don't claim success. What we claim is at least usability. Hopefully you will tell us otherwise, any of you who are doing the RL hackathon. But it's hard. So what's the right level of abstraction? What's the right level of representation of the state of what is happening? You have to understand the problem. You have to understand what the actions that matter to those who, whether it's the decision maker, what actions make sense for them. If you are, for example, modeling an environment that is, I don't know, so let's say something like a kid's bike. You're trying to learn how to ride a child's bike, right? That's the environment that you'd like to interact with. One of your actions could be, well, put a really big fan on the back and make sure that the bike just keeps moving forward, right? Technically, depending on whatever the reward function that you define, that may be okay. But in a practical sense, that's never a solution that you would choose. So you have to understand what's good in the realm of the domain of the problem that you're trying to solve, what is reasonable in that domain as well, and then tie that to, okay, now how do I share this with somebody else so that they can use it? But it's a hard problem, yeah. And the reward function piece, I just skipped that completely because it's hard. Question?
Okay, my question is more of the practical aspect.
Mm-hmm.
So, like, could you give an example where RL has been applied successfully?
Mm-hmm.
Because, okay, the way you've discussed so far, it's like it could fail, it could and it can fail.
Yeah.
So, like, could you give an example where it has been applied and it can be like relied on? Maybe it's an application or something that the builders have confidence that this agent will do the right thing or will not like.
So implicit in your question is a question. What is the definition of failure?
Not achieving the goal.
Exactly. So there is the goal of accomplishing the task that you were asked to accomplish. That's separate from actually being able to do the task well. So I will, on the screen right now is actually an example of an old RL application. Many of us have used elevators, if not all. We don't think about what is the controller that actually was used to make sure that this elevator goes to the right place at the right time. This was framed in an RL setting. What are the states? The buttons, how many times somebody actually pushed a button, whether a button is pushed right now, the position and the direction of each of the cars in the elevator lift, in the, you know what I mean? The number of passengers in the elevators, and the number of passengers that are waiting for an elevator, right? All of those are things that are used to determine or define the state of the system. Actions. For elevator number 1, 2, 3, or 4, do you stop at the next stop or not? Right? Actions. Or do you skip it? And then finally, in this case, the way that this particular problem is framed, your rewards were really more like penalties, where you were penalized if people were waiting for a very long time. So the longer somebody waits, the more penalty there is for the system, so the more negative reward. This is an example of a framing of a problem in an RL sense, so that you can learn what is the best thing to do. So when I say failure, what I'm talking about is maybe you don't find something that is the best to do. Maybe your controller, the best controller that you find is terrible. That means that you just don't implement it in something that people are actually going to use. It doesn't mean that if you step into the elevator that you will fall or something like that. What it means is that maybe the rewards associated with what you are able to find mean that people are waiting 20, 30 minutes on average. That is not a good operation for this agent. However, maybe somebody else has implemented their algorithm and they have been able to learn an agent that is able to keep the waiting time on average to a minute or two. All right, so you see the difference between if reinforcement learning works at finding a solution versus actually applying it. You see what I mean in terms of the differences of the concept of failure? Yeah, but there are many like this. So reinforcement learning is probably behind the scenes in any app that is doing prediction or updates of projections of how long is it going to take for you to get from A to B. So whether Google Maps, Waze, Taxify, Little Cab, they probably are all using RL under the hood. There are specific types of RL algorithms known as temporal difference algorithms that are the usual suspects for those kind of tasks. When you have to figure out what's the best route that you recommend for somebody, given traffic, given the uncertainty about what's ahead, squarely RL. Yeah. Cool. With that said, I can release you because I don't want to keep you from anything that you may have, but I am here. Zindi is here. Why is Zindi here? Because they're awesome. But more importantly, they're working with us to host an RL challenge. If you haven't participated, there's still time, you can still register. But the goal is for us to show practical applications of RL to problems that you might care a little bit more than playing chess or making an elevator operator. All right, thank you for your time. Hey.
Amazing talk.
Cool, cool.
Super nice.
I'm hoping it makes sense.
Completely sense.
Yeah.
I wish more people will talk like you.
Okay,
Really.
okay,
You
okay.
make it
Cool,
very simple.
cool, cool.
I wanted to ask something.
Yes.
Thank you very much.
Cool, cool.
So, as a human being,
Yes.
if I know how to play 2 or 3 games with cards,
Yeah.
if I go to another play with cards,
Yeah.